Hello everyone. In this video we're going to be stating a nonlinear optimization problem relying on the so-called KKT conditions coined after Karus and Tucker, three researchers that independently in the 1940s, 50s came up with this formulation. We're going to take advantage of all what we've seen on the previous videos to formulate the problem, which is nothing very different from what we've seen in constraint optimization. So the idea is that we have to minimize a function f of x, right, subject to a set of equality constraints, right? This j belongs to the set of equality constraints, and also a set, and this depends in principle of x, a set of inequality constraints, right, in which we are forcing the system of x to be, or c of x to be greater or equal or lower or equal than 0 or a given value for j in a set of inequality constraints, right? And in this particular problem, which is an extension of the previous one, we would be again formulating our Lagrangian on x lambda as the function we want to minimize, or in this case minimize or maximize, minus lambda transpose equality c equality, right? We substitute j by c equality just for the sake of clarity, minus lambda transpose inequality times c inequality, right? So these constraints would be c equality, and these others would be c inequality. And notice that the inequality constraints might be inactive, right, in which case we don't have problems, or active, which in that particular case they work as if they were equality constraints. So what we're going to do here is basically first, and these KKT conditions provide first order guarantee of optimality, and in this case we take again the gradient on x of our Lagrangian x lambda and make it equal to 0. Then gradient on lambda equality, right, for x lambda, sorry, vectors, and then make it equal to 0. So here I have that my equality constraints are equal to 0. These in principle depend on the state vector. And on top of that, I also have my inequalities to be greater or equal than 0. And then I have my lambda inequalities that are greater or equal than 0 as well. So these two guys must be greater or equal than 0. And the multiplication of lambda inequalities times c inequalities must be equal to 0, in such a way that if the constraint is active, meaning that c is equal to 0, then lambda can be whatever, typically greater than 0. But if my inequality is inactive, so we are within the valid domain but not hitting the boundary, then lambda inequality must be equal to 0. And when lambda inequality is equal to 0, we are in a the type of problems we were seeing for constraint optimization, right? When the lambda values get active or inactive, that's a problem we need to figure out, because there is a sequence of active inactive arcs, and that might be problematic. Just to give you an example with an aircraft in flight, right? An aircraft, imagine we are throttling, and we have a maximum throttle and a minimum throttle, right? Whatever my throttle regime is within those bounds, but not hitting them, I'm fine. I am within valid bounds. But whenever I hit the maximum, for instance, then the maximum throttle becomes an active constraint. So I want to minimize the fuel consumption of an aircraft or the flight direction of an aircraft, subject to inequality constraints that tell me that the thrust should be within the minimum and the maximum value. And that's pretty much an illustration. So now in order to solve also, these are first order conditions, KKT conditions. Then of course you need to look at the second order conditions to actually figure out whether this is a maximum or a minimum. And these are type of problems we can envision to solve with nonlinear optimization solvers. So thanks very much for your attention.